Oops, sorry.
Okay, so, by the way, I'm told that this thing is a little bit unstable. All right, we were talking about the singular value decomposition last time, and we had pretty much finished it, and we've done an example. A numerical example. And now I wanted to apply it to systems of linear equations. And so suppose we have something like this. We have some linear operator A and some vector Y, and we want to find a vector X that satisfies this equation. So what we do, and this A, we're thinking here that this is an n by n matrix. So we use the SVD expansion for A, which is a sum n equals 1 to the minimum of m and n of m sub n, s sub n, n. And so then this equation is Ax is then the sum on n, m sub n, the singular value s sub n, and x is equal to y. Okay. These vectors are orthonormal, and so taking the inner product with m sub n from the left, or let us say m sub, to be perfectly general, m sub k, we have a sum on n, m sub k, m sub n, s n, and x equals m sub k, y. This would be delta k n, delta k n, singular value n, and x equals mk y. And so we would just have the result that s sub k, k, x equals m sub k y. Okay. Now, if sk is non-zero, then we just divide through and we say, so if sk is not equal to 0, we know it's non-negative, so if it's actually positive, we have kx is equal to mky divided by sk. On the other hand, if there's a value of k such that the singular value is 0, but this matrix element is non-zero, then there's no solution. You can't have a solution. You have to divide by 0. Or equivalently, there's no way you can take 0 times something equals something finite. So, on the other hand, if it's true that the singular values are always positive when the inner products of y with mk is positive, then you can solve in that way. Okay. Now, as I said, this solution is not always available, and it's not always unique. It's not available if these SKs are non-zero. Zero. I mean, some of the singular values are 0, where these ones are not. Another example would be to take this matrix A, and here this notation is going to be a little bit of a hybrid notation. You know, we've been sort of nourishing this precious distinction between operators and matrices and between vectors and the columns or rows of components. Here I'm going to be a little bit sloppy, so I'm going to have a vector R1, R2, R3, P1, P2, P3. So suppose A is a 3 by 2 matrix like that, and suppose the vector Y is the cross product R cross P. Well then, the matrix, the system of linear equations, AX equals Y, just is not going to have any solution at all, because Y is, because AX here is a linear combination of R and P. So AX is some AR plus BP, whereas R cross P is a vector that's perpendicular to R and perpendicular to P. So RY is R dot R cross P, and that's 0, and PY is P dot R cross P is 0. And of course, R cross P is a vector whose, I'll rewrite it this way, R cross P sub I is epsilon ijk R j P k summed over j and k equals 1 to 3, where epsilon is that epsilon ijk. By the way, one of the students asked me about that. Remember, epsilon 1, 2, 3 is 1. All cyclic permutations of that are also 1. So epsilon 2, 3, 1 is 1. Epsilon 3, 1, 2 is 1. On the other hand, it's totally antisymmetric. So epsilon 2, 1, 3 is minus 1. Epsilon 3, 2, 1 is minus 1. Epsilon 1, 3, 2 is minus 1. All other epsilons are 0. In particular, if an index is repeated, the thing is 0. So I'm just mentioning that parenthetically because it's relevant to one of the homework problems. Okay. Now, so even on the other hand, when the matrix is square, if A is a square matrix, you don't necessarily have solutions to this equation. And if you do, they're not always unique. For example, if A were the square matrix that was just 0, then clearly that would have no solutions if Y is not itself a 0 vector. Let's now look at the case where n is greater than m. So consider the matrix equation AX equals Y, where now we have for A, ABC, DEF, and now a vector x1, x2, x3 equals y1, y2. Well, how about this equation? Well, once again, we would have this type of a solution, and we would say then that x would be the sum on n from 1 to minimum of m and n, m sub n y over Sn times the vector n plus a sum n equals m plus 1 to n of x sub n n. So in other words, we would have some of the vector x would be, well, as long as all of the singular values are non-zero, or all the singular values are positive, then we could write the solution in this form, but we could always add extra vectors here, because you see here we can always find vectors. In this particular case, for example, this is a 3-vector. We can always find 3 vectors that are orthogonal to any 2 3 vectors. In fact, if you take the cross product of ABC with DEF, that would give us a 3-vector that was orthogonal to both ABC and DEF. That vector then would be mapped into 0, and so if AX equals Y works for this part, then this extra part would just get mapped by A into 0. Okay. So in this particular case,
is that true when you're applying A to it?
yeah, A would map it into 0. In other words, we're looking for solutions of this form. And so, for example, what would this be? This would be, A would be a sum M sub n, Sn, n. And now we say that X is this sum n equals 1 to whatever this minimum is. M, and maybe I should use a different index, K. M sub K Y over SK K plus a sum, say n prime equals m plus 1 to n x n prime. So this one would then give us delta nk, the sk's would cancel. M sub n, that would be mk, m sub ky, and this effectively would be the vector y. Okay. So this shows that it's a solution, but all of these things, this n prime would be orthogonal to all of these n's, for which, in other words, this is n equals 1 to the minimum of n and n, whereas this sum goes from n plus 1 to n. This is the case when n is bigger than n. So these coefficients here would be arbitrary, because all those vectors get mapped by A into 0. So for any vector x of that form, we would have AX equals Y. So the solution would not be unique. Okay. Now, in the standard model of particle physics, there's the quark mass matrix. And this is a symmetric matrix M. So M is equal to M transpose. And the right singular vectors, well, an M dagger consequently, would be equal to M star. And so the right singular vectors would be given by this equation. I was writing this last time in this form. The singular values for square are the eigenvalues of the matrix A dagger A, or in this case M star M. And the left singular vectors are eigenvectors M sub n of n star, which is the same thing with n star. And on the other hand, these then are also Sn squared m sub n. That is to say, if you take the complex conjugate, this thing is positive, you take the complex conjugate of this equation, you then have, in other words, you have the equation star n star equals Sn squared, that's positive or non-negative, n star. So we can set the vector m sub n equal to the vector n star. So the left singular vectors are the complex conjugates of the right singular vectors. And this means that the unitary matrix V is simply equal to the complex conjugate of U. And so the single value decomposition, which would be U sigma V dagger, is then U sigma, and V dagger would be P star transpose, which would be U star transpose, which is transpose. So this would be U transpose. So that's, and the quark masses then are the non-negative singular values, or the singular values, whether negative or not, whether zero or not, of this matrix. So they would be, in other words, n1, n2, dot, dot, dot. Okay, it turns out that by redefining the quark fields, one can arrange for this matrix U, the matrix that occurs in the singular value decomposition of quark mass matrix. One can arrange for this thing to be real apart from one phase. And that phase is it causes a violation of a symmetry that's a combination of parity and charge conjugations. And it's called CP. So this violates CP symmetry. And this matrix is called the CKM matrix, and it's named after the physicists who were instrumental in formulating this. C stands for Cabibbo. K and M, gosh, I don't know. There are two Japanese physicists who won the Nobel Prize for this work. The Italians were very annoyed because Cabibbo didn't share the prize. Okay, LAPACK, as I said, is software that's available online, free, and is really excellent software. And you find that some very expensive commercial software packages are just the LAPACK software copied and stuck in with headers that headers where these guys copyright the stuff because they have a comma somewhere in some meaningless way. In fact, the commercial software very likely is typos, whereas I think the LAPACK stuff is tested and is correct. Anyway, rank of a matrix. Questions? Rank of a matrix. There are three equivalent definitions of the rank of a matrix. Number, linearly independent rows. Okay, rank of the matrix A. 2, number linearly independent columns. 3, number of rows or columns of the biggest square submatrix that's non-zero, has non-zero determinant. So maybe I will just say the size of biggest square submatrix of A with non-zero determinant. Okay. What?
By size, you mean number of elements or dimension?
Good point. I meant n by n. And so it's the n by n. So I guess that's why I wrote it the way I did in the notes. It's number of rows or columns in the biggest square submatrix A that has non-zero terms. So these are 3 equivalent definitions of ranks. If you in books on linear algebra, you can find proofs that one is equivalent. Each of the 3 implies the other 2. I'm not going to do that, but I will give an example. So let's look at a matrix. A equals 101 minus 2, 2, 2, 0, 2, 4, 3, 1, 1. Okay, let's look at this. It has 3 rows, so the rank is less than 3. Now, twice the first row plus thrice the second row equals twice the third row. So that is 2R1, which I guess I should write as a vector, plus 3R2 minus 2R3 equals 0. Okay. So in other words, the 3 rows are linearly dependent. That means now that the rank is less than or equal to 2. On the other hand, the first 2 rows are obviously not parallel, and so the rank is equal to 2. So that's one way of thinking about this.
Why would you write over rank of the matrix? Why? I mean, what is that?
Well, okay, good question. The rank of the matrix tells you how many linearly independent rows and columns you've got. So, and that's relevant, right? That's important. For example, suppose, I mean, this thing has rank 2. That means that although you have 3 rows, they only span a 2-dimensional space. Because the 3 are linearly dependent. And so those rows span a 3-dimensional space. Consequently, you always find a vector, a 4-dimensional vector, that A maps to 0. And in fact, you can also find a 3-dimensional vector that A maps to 0 from the left. And I think that vector is just 2, 3, minus 2. So 2, 3, minus 2, in other words, on 1, 2, 4, 0, 2, 3, 101, minus 2, 2, 1 should be 0. I'm sort of extrapolating, so not in the notes. You see, certainly this column is mapped into 0. This one would give 2. Let me do the first column. This would be 2 plus 6 minus 8 equals 0. Yes, okay. And this one would be, that one also goes to 0. And this one is minus 4 plus 6 minus 2. That also is 0. So this, in fact, is true. So in other words, you can find a 3 vector from the left that this maps 0 and a 4 vector from the right that it maps into 0. So that's what you learn about from the ranking to. Any questions?
That's because the rank is smaller than the number of columns?
Yes.
Okay.
The number of rows and the number of columns. It's half the number of columns and 2/3 the number of rows in this particular case. By the way, when I was a graduate student, first year graduate student, as a professor, he always said, she frequently said, in any particular case, and so students had pools for how many times you could say that in each lecture. I never entered any of the pools, but I know that I was carefully taking notes if they had a quarter or 50 cents or $3 or something in the pool.
So the rank is the number of basis vectors it takes to create the columns?
Or the rows, yes. All right. So the next topic is the direct product. Now this is a simple idea, but the first time you see it, it can be puzzling. And so it's good to see it now before you see it in your quantum mechanics course. So this tensor product it's also called the direct product. And it's basically that you have two spaces and you have two linear operators, one acts on one space, the other acts on the other space. That's all it is. So, for example, suppose A is an n by n matrix. Elements Aij. And now lambda is a k by L matrix. Elements lambda alpha beta. So I'm using Greek to say that that's the other operator there. Direct product, C, A, and it's written this way, is an MK by NL matrix. With elements C, I alpha, comma, J beta equal to Aij times lambda, whoops, that's a lambda. Lambda alpha beta. Okay. So that's how it is. And now what does this direct product matrix do on some vector? Well, it would map a vector V into a vector W, where Wi alpha will be a sum j equals 1 to n, sum beta equals 1 to L, Ci alpha j beta Vj beta. Okay, so that's how it works, and equivalently, that's the sum j equals 1 to n, sum beta equals 1 to L, aij, lambda alpha beta, vj beta. So that's basically, that's how it works. Now, of course, the most important case is when all these matrices are square. We don't normally, quantum mechanics, at least, in general in physics, we normally have square matrices. And the key idea is that it's a product of two operators that act on two different spaces. And that means that the A only acts on this index, and the lambda only acts on that index of the vector. So, thinking in terms of operators, A acts on some space A, and let's just say that A, let's go to the case where A and lambda are both square, then A maps some vector space into a vector space with the same dimension, and I'm going to think of it as the same vector space. So A looks like this, where here I'm letting IS be a sum of basis vectors I equals 1 n, and so this then will be a sum on ij equals 1 to n a, j, j. So that's what the operator A looks like. Lambda on the other hand will be I sigma lambda I sigma. Here I'm letting I sigma equals some alpha equals 1 to some k alpha alpha now the product, so then this would be a sum alpha beta equals 1 to k alpha alpha lambda beta beta. So then the direct product is C, which is A cross lambda, such as sum ij equals 1 to n, sum alpha beta equals 1 k, and we have I cross alpha I a j alpha lambda beta j cross beta. Okay, so notice that you just have the product of the matrix elements and that product rule is the one that I wrote down over here. Excuse me? I will, just in a moment. But you're absolutely right. This begs to be exemplified. All right, let me just say a little more of this. This direct product of the two spaces, S cross sigma, is a space that's spanned by these vectors, which we can write as I alpha, or as I alpha, or as I direct product alpha. Now, this space here is typically much bigger than the space S or the space sigma. And you see that if S has dimension 10 and sigma has dimension 10, then this direct product space has a dimension 10 times 10, which is 100. So it gets bigger. It's big. And a general vector psi in this space would be of the form I equals 1 to n, some alpha equals 1 to k, psi I alpha, some coefficient I cross alpha. And these coefficients here, psi I alpha, would be the inner product of psi with, well, I wrote 2 vertical bars there, which is kind of silly. It's the same thing as I cross alpha. Now notice that the general vector then in this space, this is in the space S cross sigma. This is in the 10 by in the case where this is a 100-dimensional space. There are 100 coefficients here. And this is bigger. This is a wider choice of vectors than just the direct product vectors. In other words, if S is a vector in X and sigma is a vector in sigma, then the vector S cross sigma, you see, is just going to be Si I equals 1 to n cross some alpha equals 1 to k sigma alpha alpha. And so this is the sum I equals 1 to n alpha equals 1 to k Si sigma alpha times I cross alpha. Well, here there are again 100 coefficients, but they're made out of 20. Wow, that thing is
there's
something
something
like
wrong. It's going back in time. It's like going, well, not now, but yeah, so every now and then it pops back to the previous frame.
I don't know what to say about that. Anyway, you see there are only really 20 coefficients here. Si and 10 sigmas. So, I mean, there are actually 100 coefficients, but they're made out of 20 independent coefficients. Whereas in general, there are 100 independent coefficients. So that means the space is much bigger than just what you get if you were just taking direct product of vectors. All right, let me see if I can pull on this. Okay, now I'm going to do the example that Tom, something funny is happening here. Sometimes the screen, on the computer screen, as I'm lecturing and we're recording, the images jump back and forth, and one student says that they're going backwards in time. Well, all right, I can do that. You want me to do that and see if it persists? All right, fine. All right, let's stop and